Okay, now this lab is lab 5. And we are going to be using the computer to measure everything. Now if we watch the video that we're going to analyze, let's just watch it. What we can see from this guy is that he is one of the worst basketball players in the history of the game. He not only missed the shot, you can't even see the basket anywhere. This guy is just plain awful. Now what we're going to do is look at him staring at you like an idiot, isn't he? Okay, so what we're going to do here is we are going to try to analyze this data. Now the first thing is these are the controls right here, but if you want to get good data, what you can do is you can make the whole thing, stretch it out nice and big like that. Alright, and what you do is the first thing you do is you set the scale. This is a very important step, and we said that the guy is 2 meters tall, so let's bring it back to the beginning. Alright, and let's give him a little, let's let him stand up straight. Let's play it a little bit, maybe to there. That's where it looks straight. And then what we do is we measure, we hit this button up here, photo distance, it's this one with the ruler, and then we go from this top of his head, we draw a line, and we draw it straight down to the bottom of his feet. Make sure it's straight down, okay? And then what we do, then we hit the ruler button, and it's not coming up. What we do is, this isn't working right. I did something wrong. What did I do wrong? I hit the wrong button. I didn't hit not supposed to hit the photo distance button. You're supposed to move one up and hit the set scale button. Don't make the mistake I made. So let's do that. Now we hit the set scale button. We draw the line just like I did last time. And it asks us, how tall is he? And we're going to say that he is 2 meters tall, okay? Now, people always ask me this set origin thing right here. Where do we set the origin to? Guess what? It doesn't matter. You could set it here, 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 here. I don't care. It doesn't matter. It's not used really. So let's not obsess about that, and let's start to do this thing where we add the points. So what we do is we move this this thing here till he's just leaving his hand. All right, right like that. It's just leaving his hand. And now we're going to add points. And what you do is you click on the Add Points button up here. It's the second one from the top. And you click on the center of the ball. And then you click on it again. Each time it's going to advance 1 frame. So we click on the center of the ball. We click on the center. You notice there's data appearing over here. All right, so we click on the center of the ball and we keep clicking on the center of the ball. And it's taking data. And we keep doing it. And we keep doing it. We're getting lots of data. This is really easy, isn't it? I never really understood why anybody had trouble with this particular lab. A lot of people finish it real fast, like in an hour, hour and a half. And you keep going, and you keep going. I'm doing a little bit carelessly, but you just do it in the center. You notice it's getting faster each time. Okay, that's good enough. Alright, so now we shrink it back down. Now what we're interested in is what we're trying to figure out for the first one is the acceleration. Well, how do you figure out acceleration? Well, we have a velocity plot here. Acceleration is the slope of velocity. So let's select a bunch of data, and then because we hit stat, right? Wrong! Wrong! Don't do it! Don't do it! Don't! No! Don't hit stat! It's not a stat problem. We're supposed to hit the R equals button up at the top, which is a linear fit. Not the stat button, because it's not flat. So don't use stat. Anyway, it will tell you, in my case, I got a slope of negative 9.893. Now when you fill out your form there, it says to put it as absolute value, just because I don't want some people putting negative, some people putting positive, so just put 9.893 or whatever you get. Easy enough. Okay? Now the other thing it asks you for is the initial velocity in polar coordinates. Well, to do that, first we only have velocity in the x and y coordinates. So let's take the initial velocity in the y, and the easiest way to, that one changes. Okay, if you look at this, it starts up here and goes down, 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 down until it goes negative. It's falling. So we just want the first point. In my case, I got 4.317. Now, in the case of the x velocity, it doesn't change because the velocity of x and y are independent. All right? So what we can do there is, guess what? It is flat, so we can use stat. And we get 3.174. So if we take our data, then all we really have to do is just draw a triangle. Here's our x, here's our y. All right? And to get it in polar coordinates, we have our Vx, we have our Vy. So then, what we do is we say, well, Vr is just going to be the square root of Vx squared plus Vy squared. Easy. And the angle, this angle right here, is just going to be the inverse tangent of the opposite, in this case Vy, over Vx. Well, that's easy. Okay, so now we're done with part 1. Now in part 2, it's a car crash. Everybody stare at the car crash on the side of the road. Well, not quite. All right? It's actually it is a car crash. I'm going to load it up here, and then I will show it to you. Give me a second. One more second. I said one more second. Just give me a second, okay? Vlogger Pro for a car crash. Okay. Now, if we watch this video, let's make it big too. You see the car. Okay. We hit the play button down at the bottom, and bam, it hits there. Look at that car. Okay, the important thing here is this car is obviously going in slow motion, so we're scaling it not only in space like we did the first time, and you remember how important that was, or you will know, we're also scaling it in time. So if we look at this car, there's 3 different regions where it's going here. Right in here where it's going at a constant velocity of 30 meters per second. All right? And then right in here where it's slowing down because it hit the wall. All right? And then over here at the end where it stopped. We don't really care about that. Now what you're going to do is you're going to do the same thing you did in part 1, and we're going to track this little white spot on the car. It's right there. Okay? And it's pretty easy. You just we're going to scale it, right? We've got the scale here. Set the scale. I think this is it. 1 meter. I think. It doesn't really matter for now. I'm just showing you how to do this. All right? And then we start taking data. Boom, 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 boom. It's going along at 30 meters per second right here. It's very important. Watch this video a couple times if you don't get this. One second. Okay? And then it's hit. Now right here is where it's going to hit. So we're going to go off into region 2. Okay? And you see, if you look on the data suddenly, the velocity is changing. And we keep going, and we go till we get to, it stops. That's good enough right there. So now let's take a look at our data. And you can see here's region 1 where we know it's going 30 meters per second. And here's region 2 where it's slowing down because it hit something. Now here, if we look at it though, if we take the stats on this flat part right here, it says that the mean is 0.6277. This is because of the scaling in time. And if you look at your data sheet, you have to figure out your time scale factor, CV, which is going to be equal to 30 divided by this. Then you can figure out what your acceleration is in this part here, Because right here is where we're interested in the acceleration in region 2. And we figure, okay, here we're going to need to figure out acceleration velocity. So again, we use the R linear fit. And we get the slope. All right? So now we have the slope, and it says 0.4706 meters per second squared. But that's not accurate because we didn't take into account the time scaling factor. So what you have to do is you have to multiply it by CV squared. All right? Now we want to figure out the force. Beware the dark side, Luke. Oh, not that kind of force. The force, it's going to be the mass times the acceleration. Well, the acceleration is going to be this times that CV squared factor. The mass, well, we know the car weighs 20,000 newtons. So it's going to be 20,000 times the acceleration, right? Wrong! 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 The weight of the car is 20,000 newtons. The mass of the car, weight is equal to mg. So the mass of the car is going to be 20,000 divided by 9.8. Don't make that mistake. That would be bad. And you get a number for the force, and it's going to be a big number. If it's not a big number, you did something wrong. Okay? And then people always ask me, I got a big number, is that right? Yes. Don't ask now. All right. Next, the question on that one is, does every point in on the car experience the same force? Well, think about it for a minute. If you were in this car accident, where would you want to be sitting? Would you want to be sitting on that front bumper? Or would you want to be sitting in the back of the car? Obviously, you'd want to be sitting toward the back. Why? Because the forces are lower. Now, can you prove it to me that the forces are lower? There's a couple different ways to do it. I want you to think about that before you come to class. Are you thinking about it? Okay, that's enough. Think about it some more later, too. Okay, for parts 3 and parts 4, they're pretty easy. Okay? All they do is the same kind of thing. I hope I'm focused on this one. I'm doing this myself. They're just using billiard balls. Okay? Now, in that one, you're supposed to see conservation of momentum. Okay? But you won't, because what we're doing there on the billiard balls one is we are measuring the translational momentum. Now, momentum is always conserved, but there's two parts to it, translational and rotational. So what happens? Well, as it turns out, the translational plus rotational before is equal to the translational plus rotational after. Okay? But since we're not measuring the rotational momentum, we're only measuring the translational, what happens is some of the translational becomes rotational. All right? So that's why you're not going to see it conserved. Now in the last part, if it works, because a lot of times it doesn't for various reasons, you're going to see that the momentum will be conserved because there's only translational momentum. Oh, one last thing about the third one. People always ask me about that. How can I get the momentum for both balls at the same time? Well, you can do it if you really know what you're doing with Logger Pro, but most people just do the video twice. One time they use one ball, one time they do the other ball. There's the velocities. Boom, you're done. Okay? Any questions? Well, too bad because I can't hear them. Oh, yeah, one other thing. Somebody did leave this flash drive here. It'll be in the lost and found. Unless nobody claims it. Maybe I'll look at it and make fun of whoever's on here. Okay? So, have a great day. It's going to be a busy day. I know. Bye.